Okay, this is the second trial video for the chemistry department. This one is on how to convert empirical formula into molecular formula, and in the second half of the video I'll show you how to go through calculating the formula of hydrated salt. So if you're looking to do this conversion, you have to look at taking the empirical formula, which in this case has been given to you as CH, and converting that into the molecular formula, i.e. how many of each type of atom you have in that molecule. The other bit of information you need in order to do this is the molecular mass, which in this case is 78. So what you need to do is you need your calculator and your periodic table to hand. And first of all, look at your mass number or relative atomic mass of carbon and hydrogen. So carbon is 12, hydrogen is 1. We have one of each of those, so we get to 13. So 1 unit of that molecule is 13. However, the whole molecule weighs 78. So we need to work out how many lots of 13 there are in 78. So you can have 78 divided by 13, and that comes out as, if you just type it into your calculator, comes out as 6. Therefore, if the empirical is CH, the molecular formula is 6 lots of CH. So we would write it C6H6. So a second question down here. Again, you've been given the empirical formula. This time it's CH2. Again, you've been given the molecular mass, 42. So just follow exactly the same recipe that you did beforehand. So the carbon, look that up, it weighs 12. Hydrogen, look that up again, weighs 1. But this time we have 2 lots of hydrogen, so it's going to weigh 2. Okay, so 2 lots of hydrogen, and that comes to 14. How many 14s do we have in 42? So 42 over 14 comes to 3. So if our empirical formula is CH2, our molecular formula is 3 lots of CH2. So 3 lots of 1 carbon is 3, 3 lots of 2 hydrogens is 6. So we've got C3H6, which you should probably be able to tell me C3H6 is propene. So on to the next slide. We might have to do it from scratch. We might have to take our masses and then calculate an empirical formula and then use that to calculate its molecular formula. So here it says calculate the empirical formula, but we should also add and molecular formula. There, terrible handwriting. So think back to what we did last time. How do you calculate the empirical formula using these masses here and here? Well, the first thing you need to do, you should be doing this sort of automatically now, is drawing up a table. Phosphorus on one side, oxygen on the other. You've got 0.282 of phosphorus, you've got 0.218 of oxygen. And the first thing we do, divide by the RAM. And the second thing we did after that, the second division, was divide by the smallest. So, RAM of phosphorus, look it up on your periodic table, 31. Oxygen, 16. And if you do that calculation very quickly, 0.00910, and for oxygen, 0.0136. Then you have to divide by the smallest. Well, this one here is the smallest, so that divided by 0.00910. Do the same thing to the other side, 0.00910, and that gives a ratio of 1 to 1.49. Effectively, 1 to 1.5. Now that's not good enough as a ratio, we need a whole number ratio, so if we scale both sides up by, well, let's say we double both sides, we effectively get to 2 and 2.98. 2 to 3. 2 to 3. Bit of a typo. So our empirical formula, okay, is P2O3. I'll do the molecular formula calculation in a different colour. So now we're at the same point that we were at with the previous questions. Now we have to work out how much 1 unit of that empirical formula would actually weigh. So phosphorus, well, we've got 2 lots of phosphorus, so it's 31 and 31. 3 lots of oxygen, 16, 16, 16. Okay, if we add all those together, we get 110. Now we've been told its molecular mass is 220. So how many times does 110 go into 220? And even with my maths, I can work out it goes in twice. So we go from having its empirical formula of P2O3 to its molecular formula, which is double that, which is P4O6. And that's how to calculate a molecular formula all the way through from the very start, where you've just got reacting masses together. Now, examiners sometimes at GCSE and at A-level ask you to calculate the formula of a hydrated salt. And it just follows a very similar process than you use for an empirical formula calculation. So here we have a hydrated sodium sulfate salt. We've got hydrated crystals here. And if we heat those to a constant mass, so in other words, where no more water has been given off, I'll just put the equation down very briefly. So we produce sodium sulfate anhydrous and n lots of water. So we heat it to a constant mass and then weigh the sodium sulfate which is left. And we can then use this information to calculate our empirical, well, actually it's not an empirical formula, it's the formula of the hydrated salt. But you do it in the same method, you do it the same way as you would do an empirical formula. So you start off with a table, and rather than putting the elements in each column, this time we're looking at the ratio of sodium sulfate to water. So in this column I'll have sodium sulfate, here I'll have water. We need to work out how much water we had. Well, 5 grams of what we had in total produced 2.2 grams of sodium sulfate, and the remaining mass must be water. So 5 grams take away 2.2 grams gives 2.80 grams. Think about what we did next with the empirical formula calculation. Well, the next thing we do is divide. Well, last time we divided it by the atomic mass. Here we divide it by the formula mass. And the second division was dividing it by the smallest. So it's the same kind of thing. So this time we need to calculate our formula mass of sodium sulfate. So have a look at your periodic table. Sodium, well, each one weighs 23. Sulfur, well, let's just jot it down over here. So we've got 23 and 23. Sulfur is 32. And each oxygen weighs 16. Okay, and that comes to, get your calculator out, 142. So this time we divide by 142. Water, much quicker to work out. Oxygen, mass of 16. 2 hydrogens in there, so 16 plus 2 gives 18. And if I plug those numbers into a calculator, I get 0.0155. And on this side, 0.1556. Again, we divide by the smallest. And that gives a ratio of 1 to 10.0. So our formula is Na2SO4 dot 10 H2O. And hopefully you can see that it's exactly the same method as we used for our empirical formula. One more. Here we've got copper sulfate. Again, we heat to constant mass, and again we're asked to calculate the formula of our crystals. So again, draw the table, and on this side of the table we're going to have CuSO4. On this side of the table we'll have water. So they've told us that we have 18 grams of water, and they told us we've started with 49.9 grams of the hydrated crystals. So this is the anhydrous crystals, the crystals without the water. So 49.9 take away 18 gives 31.9. So here we go, 31.9. Now, again, think about what your next two stages of the calculation are. What do we do here? Well, here we divide, and here we divide again. So what did we divide by here? We divided by the formula mass of each one, and our second division we divided it by the smallest. So copper sulfate, again we've got to do a bit of a calculation, get your periodic table out. So find your relative atomic mass of copper, which is 63.5. We've got a sulfur in there, which is 32, and we've got 4 oxygens, 4 lots of 16, which comes to 64. If we add that together, we should get 159.5. Water, oxygen 16, hydrogen 2, 18. So if we just do a quick calculation on that, that gives 1, 2, 0.2. Again, we have to divide by the smallest. This one is the smallest, so 0.2 of 0.2, 1 divided by 0.2, and that gives a lovely ratio of 1 to 5. Again, finish the question off, so you put it into the format of our formula, CuSO4 dot 5H2O. And that is the finished answer, and that is how to calculate the formula of a hydrated salt.